Hello, this is Module 10, LAN Security Concepts. It's a chapter 2 under switching, routing, and wireless essentials. So in this module of we're going to cover these areas: um, endpoint security, then access control. We have layer 2 security threats, MAC address table attacks, and then the LAN attacks. So let's begin with endpoint security. The news media commonly covers attacks such the internet for latest network attacks to find the up-to-date information on current attacks. So most likely, these attacks will involve one or more of the following. So this is just the why you can manage. Then search for latest network attacks. Latest network attacks. So this they're saying the news media commonly covers. So most of the time, this is the attacks that are will. So we have distributed denial of service, we have data breach, we have malware. So distributed service, denial of service, this is a coordinated attack from many devices. So if the attack is actually from the many devices, then it's called zombies, with intention to degrading or altering public service. We have data breach. This is an attack in which an organization's data or hosts are compromised to steal confidential information. Malware, this is an attack in which an organization's hosts are infected with malicious software that cause a variety of problems. For example, ransomware such as WannaCry encrypts the data on host and then locks access to each until the ransom is paid. So network security devices that are available that you need to look for in case you want to implement security. We have virtual private network, the one we call VPN, enabled router. We have next generation firewall that provides stateful packet inspection. It inspects the packets as they are entering the network. So this is next generation firewall that provides stateful. It inspects the packets before they enter the network. Then we have even the next generation intrusion prevention. For this one here, it prevents. The first one here, it inspects, and then this one here, it prevents. And then we have advanced malware protection for protection, and then we have URL filtering. We have another device called network access control. Includes authentication, authorization, and accounting services. In large enterprises, these services might be incorporated into appliances that can manage access points across wide variety of users and device types. So endpoint protection hosts with which commonly consist of laptops, desktop. Those are the endpoints. So every time you're trying to protect the endpoints, then you're dealing with desktop servers, laptops, IP phones, as well as employees that the employee-owned devices. So endpoints have typically used traditional host-based security features, where we have antivirus and malware, host-based intrusion prevention system, the ones that are actually host-based per device, not the entire network. So endpoints today are best protected by combination of the network access control, the advanced malware protection software, and then email security appliances, and web security appliances. So these are the devices that are actually part of the network specifically to provide uh, protection on the network. So this is just a Cisco email security appliance designed to monitor simple mail transfer protocol. This one here is for monitoring, for monitoring the emails, be it that are exiting the network or entering the network. They have to be monitored. So the Cisco ESA is constantly updated by real-time feeds from the Cisco Talos, which detects and correlates the threats and solution by using worldwide database. That it is connected to database, the worldwide database that it keeps on updating, picks what are likely to be the threats in the database, and then compares them with whatever that is entering your network or exiting the network. So these are some of the functions of the Cisco ESA. It blocks known threats, the threats that are known, and then remediates against the stealth malware that invaded the initial detection, discards emails with bad link, blocks access to newly affected sites, and encrypts content in outgoing to prevent data loss. So we have what you call Cisco Web Security Appliance. Is a mitigation technology for web-based threats, and it helps the organization to address the challenges of securing and then controlling web traffic. So Cisco Web Security Appliance provides complete control over how users access the internet, certain features and applications such as chat, messaging. So you can actually use that application, the appliance, to chat, messaging, and then video and audio can be allowed to restricted with time and then bandwidth limit, blocked or according to the organization requirement. So when it comes to the chats, messaging, videos, and blah blah, so with Cisco Web Security Appliance, it can actually help to limit the chats, the messaging, videos, and then audios that are made on the network. Then we have access control. So authentication with with access control, we have authentication with local password. So with local password, it means that it's this device, for example, you protect the device, but you create the user name and then the password onto this very device that you're trying to protect. So many types of authentication can be performed on network device, and each method it offers varying level of security. The simplest method of remote access authentication is to configure login and password combination on console, VTY, and then auxiliary port. Then we have what we call SSH, which is secure shell, is more secure form of remote access. It requires username and then the password. Username, password can be authenticated locally. It's this very device that you're protecting, and that is where there is the password and the password that the username. So local database method has some limitation. User accounts must be configured locally on each device, meaning that if you have 100 devices, you have to have 100 credentials on every device. We have what we call AAA components. It stands for authentication. Have authentication, authorization, and then accounting. Provides primary framework to set up access control on a network device. So AAA is a way to control who is permitted to access the network, that is authorization, what they can do, that is authorization, while they are authorized. What can they do, that is authorization. And then lastly, the audit, what actions they performed while accessing the network. So if you deleted, up-to-dated, and blah, blah, all those logs or the events, they are under accounting. So we have under access control, we have what we call authentication. Local and server-based are two methods of implementing AAA authentication. We have local AAA authentication. Method stores the username, passwords locally on that very device that you're trying to protect. User authentication against the local database. Local AAA is ideal for small network. For small network. Then we have server-based AAA authentication. With the server-based method, the router accesses a central AAA server, and then the server contains username and then the password. Now it means that the usernames and the passwords on the network, they are saved somewhere. There is a server meant for all those the authentications. The server for storing usernames and then the password somewhere for all the devices. So if there is a need for change to alter the password, to alter the usernames, so it's done on a specific server. So the router uses either what we call remote authentication dial-in user service, which is Radius, or TACAS, which is this. TACAS, it stands for Terminal Access Control System protocol to communicate with AAA server. So when there are multiple routers and switches, server-based AAA is more appropriate method to use because the changes are done on the server and then it affects all these other devices, be it a router, be it a server, a switch on the network. Then with authorization, is automatic and does not require user to perform additional step after authorization. So with authorization, like we said, it just governs what users can and what they cannot do on the network after they have been authenticated. We have accounting. We said with the accounting, uh, collects and reports the usage of data. This data can be used for such purposes as auditing and then billing. So the collected data might include the start and then stop connection time, executed commands, what you did, and then number of packets and number of bytes used. The primary use of accounting is to combine it with AAA authentication. Triple You logged into the system, what did you do? Or what are you allowed to do? And what did you exactly do? You're allowed to do this, but did you do it? You're allowed to do this, what exactly did you do? So AAA server keeps the detailed log of exactly what the authenticated user does on the device as shown in the figure. Then we have the log contains numerous data fields, including username, date, time, actual command that was entered by the user. So this information is useful when troubleshooting the device in case you have a challenge on the network. Then we have what we call the this standard or this feature IEEE 802X standard is point to. So we have this feature under access control, which is IEEE 802.1X standard, is a port-based access control and authentication protocol. So this protocol restricts authorization workstation from connecting from connecting to the LAN through publicly accessible switch port. So the authentication server authenticates each workstation that is connected to a switch before making available any service offered by the switch or a LAN. That for every device that connects on this network, it has to be authenticated. It has to be authenticated. Either is this computer allowed on this switch? Is it known on this the server? So if it is known, then automatically it will be authenticated. So it has three, where we have the client, we have the switch, we have the authentication. So the client is the supplicant. Supplicant. This is a device running this feature compliance service software, which is available for wired or wireless device. So for every device to be part of this switch, it has to be authenticated by the server. It has to be known that this application, it will have to first contact the server. So if it is allowed, then the switch it is going to accept it. If not, it won't be allowed. We have authenticator. The switch acts as intermediary between the client and then authentication server. It requests identifying information from the client, verifies that information with authentication server. That this application is going to send the information after it is verified by the server. So if it is authorized or allowed, then the switch it will allow this computer to be part of the network. We have the server validates the identity of the client and notifies the switch or wireless access point that the client is or is not authorized to access the LAN switch service. So we have what you call layer 2 security threats. Layer 2 security threats. On layer 2, we are expecting under OSI, we're expecting data link layer to deal with Ethernet, the Ethernet frames. So recall that OSI reference model is divided into 7 layers which works independently of each other. So the figure here, it indicates all the 7 layers. So network administrator routinely implements security solutions to protect the elements in layer 3 up to or up through layer 7, starting from network layer. Where is the network layer? It's this, through this. So they use the use VPN firewall. They use VPN firewalls, IPS device to protect this element. However, if layer 2, you see that all these things, security, the security settings configurations are done starting from layer 3 through layer 7. So, but however, if layer 2 is compromised, then all the layers above it are also affected. For example, if a threat actor with access to internal network to the internal network captured layer 2 frames, then all the security implemented on the layer above would be useless. So still layer 2, it has to be protected. So switch attack categories. We have marketable attacks, we have VLAN attacks, we have DHCP attack, we have ARP attacks, we have address spoofing attack, and STP. So with MAC address table, it includes MAC address flooding. Then the VLAN attack includes VLAN hopping, VLAN double tagging, tagging the double, the VLAN twice. Then when it comes to VLAN hopping, it's just creating allowing VLAN 1 to access VLAN 2 without using layer 3 device. It also includes attacks between devices on common networks. Then we have DHCP starvation to starve the DHCP service, and then DHCP spoofing. DHCP spoofing. Now with spoofing, that is when the DHCP is assimilated somewhere on an invalid device. Then we have ARP. ARP spoofing and ARP poisoning. Yeah? Spoofing and then poisoning. We have the spoofing attacks, address spoofing attack, MAC address, and then IP address spoofing attacks, and STP, spanning tree protocol manipulation. Then attacks. We have the mitigation techniques. There we can use what we call port security to implement security on ports to prevent many types of attacks, including MAC address flooding. Then we have um, MAC address flooding, and then DHCP starvation. We have DHCP spoofing, it prevents DHCP starvation, and then spoofing. Dynamic address resolution protocol inspection prevents ARP spoofing and then poisoning. IP security guard, IP source guard prevents MAC and IP address spoofing. So all these are the solutions to the previous attacks. So we have MAC address table attack. So recall that that to make forwarding decision, a layer 2 device, a layer 2 switch, it builds the MAC address table. It builds a table based on the source MAC addresses in receiving frame. This is called MAC address table. So the MAC address table are stored in memory and are used to more efficiently switch the frames. So with MAC address table flooding, all MAC address table have fixed size, and consequently a switch can run out of resources in which to store the MAC addresses. So the MAC address flooding attacks take advantage of this limitation by bombarding the switch with fake source MAC addresses until the switch MAC address table is full. And then once the MAC address table is full, then this switch treats the frame as an unknown unicast, and then it begins to flood all incoming traffic out of all ports on the same VLAN without referencing MAC address table, because the MAC address table is full. So there is no need of comparison. So whichever that comes in, it is treated as an unknown unicast and it is flooded. So this condition now allows late actor to capture all of the frames sent from one host to another on local LAN, local LAN or local VLAN. Note, traffic is flooded only within the local VLAN, local LAN or local VLAN. So the slate actor can only capture traffic within the local LAN or the VLAN. So the mitigation, what makes tools such as mark off so dangerous? Is that the attack can create MAC address table overflow attack very quickly. For instance, Catalyst switch, which is 6500 switch, it can store around 132,000 MAC address in its MAC address table. So a tool such as the one that I've mentioned, it can actually flood a switch up to 8,000 bogus frame per second. So within just a single second, then it means that this the tool mark off, it can generate up to 8,000 bogus MAC addresses. So creating MAC address table overflow attack in just matter of few seconds, just within like 3 seconds, it will be full. So another reason why these attack tools are dangerous is because they are not they not only affect the local switch, but it also affects other. They can also affect other connected layer 2 switches. In other words, it keeps on. It's a network. It networks. It networks the attacks to other device. So to mitigate MAC address table overflow attack, network administrator must implement what we call port security. So we're going to look at how to implement such port security in another session to only allow specified number of source MAC address. So you can tell, like, I only need one MAC address on this port, maybe 2 or maybe 3, but still with other methods that you're going to look at that goes with port security to prevent those attacks. We have within under LAN attacks, so the VLAN attacks. Here, this is the video that tries to cover the number of those attacks. We have VLAN hopping, VLAN double tagging, then DHCP starvation, then DHCP snooping. Here you just watch, just watch. So with VLAN hopping attack, it enables traffic from one VLAN to be seen by another VLAN without the aid of router. So it's this computer, but this is an attack, is able to actually view traffic from different VLAN. This is VLAN 10, VLAN 20, without a layer 3 device. That is what you call VLAN hopping. VLAN hopping. So then we have the what we call the VLAN double tagging. Select actor is if specific in specific situation could embed hidden tag inside the frame that already has a tag. This tag allows the frame to go to VLAN that the original tag did not specify. So this is just disguising that you, or maybe calling yourself so and so, yet you're not the one. Your real name is maybe John, but you're calling yourself James. So here on this point, they are allowing John, but on reaching the other point, you're James. Differently. So step number 1, the select actor sends double tag frame to switch, and then the outer header has the VLAN attack, the VLAN tag of the select actor. So, which is the same as the native. That the VLAN tag for the select actor is disguised as the native VLAN tag, and for that, it will be allowed on the network without being checked. Step number 2, the frame arrives on the first switch, which looks at the first 4 bytes, and then the switch sees that the frame is destined to native, that the frame is not supposed to be checked, and then the switch forwards the packet out of native VLAN in that line whereby the VLAN is not supposed to be checked. So the native VLAN port, after stripping off its VLAN tag, that tag that identifies that VLAN as native, then the frame is not retagged because it is part of the native. So at this point, the inner VLAN tag, it is still there. Remember, it is it's a frame with 2 tags, with 2 tags. So the first one here, let's assume 10, part of native. But the one for the actual slate, it's within inside. So once it crosses one of the switch or 2 the switches, then it will be allowed to be pushed to whichever VLAN that intends to reach. So the frame arrives at the second switch, which has no knowledge that it was supposed to be part of native, because in on the first switch, the frame it was identified as native, and then on the second switch doesn't, or it is not aware that the frame is supposed to be part of native. So on the second switch, it will have to have the deal with the tag for the attack VLAN or attack device, and then it will attack the intended device. So the native VLAN traffic is not tagged by the second switch as specified, and then the second switch will look only at the inner tag that the select actor the threat actor inserted and sees that the frame is destined to the target VLAN and is legit. So the second switch will send the frame onto the targeted or fraud switch, depending on whether there is existing MAC address, the table entry. So the continuation VLAN tag, the VLAN double tagging attack is an indirectional and works only when the attack is connected to port residing to the same VLAN as the native VLAN on the trunk port. So the idea is that double tagging allows the attack to send data to hosts or server on VLAN that otherwise would be blocked by some type of access control configuration. So VLAN attack mitigation, the VLAN hopping and VLAN double tagging can be prevented by implementing trunk security guideline as discussed in the previous module. Then you can disable trunking, the trunking on all access ports, disable auto trunking on trunk links, then be sure that the native VLAN is only used on trunk links. Then we have DHCP, the operations of DHCP message. DHCP server dynamically provides IP address information, including IP address, subnet mask, default gateway, DNS server, and more client and more information to clients. So a review of sequence of DHCP message exchange between client and server is as follows, whereby we expect the client to initiate the process, DHCP discovery, and then the DHCP it offers, and then once the client receives the offer, it sends a request of that offer, and then the server acknowledges it. So those are the steps, the messages that are exchanged between the client and then the server. So when it comes to attack of the DHCP, there are two types. We have DHCP starvation and then spoofing. Starvation, that is when the threat actor forces the DHCP service to lease out all IP addresses, or in other words, to run out of IP address. Then spoofing, that is assimilating false service on the network, so that the clients, when the client tries to look for the information, the information it is generated from a wrong device. So you can try to read through the statements there. You'll get all that information. So here is the video. We'll cover the following: ARP spoofing, ARP poisoning, spanning tree protocol attack, then Cisco discovery protocol recognizes. So ARP attacks host broadcast ARP requests to determine the MAC address of the host with the destination IP address. Because ARP, it maps the known IP address with an unknown MAC address. So all hosts on the subnet receives and processes the ARP request. So the host with the matching IP address in the ARP request, it sends the reply. It's the one to reply. So if a broadcast is sent with the known IP address, so the targeted computer with that very known IP address, it's the one to reply back. So a client can send what we call any solicited or unsolicited ARP reply. Any solicited. So solicited, it's a request that a client can send a request. It can send a request. Okay, not that. Okay, not. But share the request. It is in the form of reply. That a device it can send unsolicited. It's the reply that was actually not requested for, and sometimes it's called gracious ARP. So other hosts on the subnet stores the MAC address and then the IP address contained in that gracious ARP in the ARP table. So an attack can send the same, the gracious ARP message containing the spoofed MAC address to the switch, and then the switch would update its MAC address table accordingly. In a typical attack, a threat actor sends unsolicited ARP replies to other hosts on the subnet with the MAC address of the threat actor and IP address of the default gateway, effectively setting up man in the middle, that every time there is a need, then the man in the middle is the one to reply. There are many tools available on the internet to create ARP man in the middle attack. IPv6 uses ICMP version 6 neighbor discovery protocol for layer 2 address resolution. IPv6 includes strategies to mitigate neighbor advertisement spoofing, similar to the way IPv6 prevents spoofed ARP reply. So the address spoofing attack is when a threat actor hijacks valid IP address, valid IP address of another device on a subnet, or uses a random IP address. So a random IP address is a guest IP address, but IP address of the other device is the known IP address. So the random one, it may be actually active or not active. So IP address spoofing is difficult to mitigate, especially when it is used inside a subnet in which the IP address belongs to. So the MAC address spoofing attack occurs when the threat actor alters the MAC address of their host to match another known MAC address of a target host. So the switch overrides the current MAC address entry and then assigns the MAC address to the new port. It then inadvertently forwards frames the snitch for the target host to the attacking host. So when a target host sends traffic, then the switch will collect the error, realigning the MAC address to the original port to stop the switch from returning port's assignment to its collect stage. So here, this when the threat actor will actually hijack the IP address, tries to assign it to any other computer, but every time the legit computer tries to send, then there will always be realignment of which one is genuine and which one is not genuine. Yeah? And then we have STP attack, network attack. Attackers can manipulate the spanning tree protocol to conduct attack by spoofing the root bridge. So with the STP, you can, the threat actors, they can actually try to assimilate to force the root bridge on the network. You add, for example, you have, let's assume that we have this is our network, and then someone adds another switch and our root bridge is this, and then someone adds a switch here and then forces this to be the root bridge. That is what is all about STP attack. So then we have CDP recognizes, which is Cisco Discovery Protocol, is a proprietary layer 2 link discovery protocol that runs on Cisco device. It is enabled on all Cisco devices by default. The information is sent out of CDP enabled ports in periodic unencrypted authenticated broadcast. So the information includes IP address of the device, iOS software version, platform capabilities, and native VLAN. So the device receiving the CDP message updates its CDP database. So this information or this protocol, it can also be hijacked, and then the threat actor tries to or uses it to learn information on the neighboring device. So to mitigate the exploitation of CDP, which is Cisco Discovery Protocol, limit the use of CDP on devices or ports. For example, disable CDP on edge port, that connects to an trusted device. So if you have a switch here, all these ports that connects to end devices, they are untrusted ports. So you can disable CDP on all these ports. But between this device, the switch and the switch, there you can allow your CDP, CDP there. So that if you're on this router, you're able to get information from this, but not the end device. Because on these switches, when it comes to the switches, you can even go ahead and put them in rack. You hide them in racks and lock the rack. No one will ever access. But when it comes to the end, the cables that connects to the PCs, we have access. Someone will come and disconnect this cable and then connects it to the switch. So if you don't do that, then it means that you're creating the gap. So to disable CDP globally, you can use this globally. Globally, I mean like, let's assume that it's router 1, then in bracket config. That is where you can put no CDP run. If you want to enable it, you just use CDP run globally. Or you can actually disable CDP on port. So it will be just router 1 config if. In this mode, that is why you can put no CDP enable. You're disabling it on a single or a specific interface, and that makes the end or marks the end of our